Welcome all. In this class, basically we'll discuss about the gravitational field strength due to a long thread or a wire. So consider that we have a wire of some length L and mass. So in question they may give its linear mass density. Linear mass density means nothing but mass per unit length. So take it as total mass of this rod is m and its length is L. So its lambda is representing its mass per unit length, or it is known as linear mass density. And in a question, they may ask to find out what about the value of gravitational field due to this rod or thread at a point, let's say somewhere over here. So our aim is to find out the value of gravitational field at a point P, which is at a perpendicular distance r from the wire. And we are going to find out the value of gravitational field at point P. So for the calculation purpose, we need to consider a small element over here. Let's say I'm just considering a small element over here of mass, take it as nothing but dm, and this dm element is at a distance y from this point. So the thickness of this small element, we can take it as nothing but dy. So what we'll do is first we'll find out what about the value of gravitational field at point P due to this small element of mass dm. So you can write due to this small element of mass dm, this gravitational field will be along this direction. Let's say this gravitational field is represented by nothing but dg, and if it is making an angle theta, let's say we can resolve this dg into its components. So component of this dg along this direction, as we are writing theta over here, this component is going to be nothing but dg cos theta, and this component we can take it as nothing but dg sin theta. Like that, if you are finding out different elements at different points, then we'll get the different value of dg, and if you're adding all these dg components, that means if you're adding all these dg cos theta component that is perpendicular to the wire. So if you are going for integration of all these dg cos theta components, then we'll get the gravitational field which is perpendicular to the thread. And if you are going for integration of all these dg sin theta component, then we'll get the value of gravitational field which is parallel to that. So we are going to find out this value over here. Let's say first we'll find out the value of its perpendicular component while integrating this dg cos theta. So if you want to find out the value of net gravitational field perpendicular to this wire, so we'll go for integration of dg cos theta. Now this gravitational field due to small element, which we can take it as something but g into dm divided by, we need to go for square of distance. So let's say this distance over here is given as something but y, and this distance is r. So according to Pythagoras theorem, we can write this distance which is equal to under root of r square plus y square. Now if we are squaring it, so we'll get it as r square plus y square into the value of cos theta. Now from the right angle triangle, means I'm talking about this right angle triangle, we can write cos theta is adjacent side, which is r, divided by hypotenuse, that is under root of r square plus y square. So we can write it as something but this is r divided by under root of r square plus y square. Now further we can write this is equal to nothing but g into, now this dm is representing the mass of that small element. So from the equation for linear mass density lambda, we can take it as dm divided by dy, that is mass per unit length. Instead of this dm, we can write this as lambda into dy into r divided by this r square plus y square, and under root of r square plus y square, which is r square plus y square raised to 1 by 2. 1 plus 1 by 2 we can take it as 3 by 2, so it's going to be r square plus y square raised to 3 by 2. Now if we are going for integration of this, we will get the value of net gravitational field which is perpendicular to this wire. So over here you can observe that this g is a constant, lambda is a constant, and this r is a constant, and over here this y is a variable, so we need to integrate this term dy divided by r square plus y square raised to 3 by 2. Now for integration of a function something like this, we'll take this integration by substitution. That means we'll take it as this y is equal to r tan theta. So from this like triangle also we can just observe that this distance is nothing but r, and this distance is nothing but y. So we can write this tan theta is equal to y divided by r, or you can write y is equal to r tan theta. This is a method for integration of this type of questions. So you can write the value of dy is equal to r into differentiation of tan theta is sec square theta into d theta. So we can write the component of gravitational field perpendicular is equal to g lambda into r into integration of, instead of dy we can write this as integration of sec square theta d theta divided by r square, instead of r square plus, instead of y we can take it as r tan theta, so it's y square becomes r square tan square theta raised to 3 by 2. So this can be again written as g lambda into r, and this r also we can take outside, so this is g lambda into r square into integration of sec square theta d theta divided by, if you are taking this r square common over here, so it is going to be r square raised to 3 by 2, that is r raised to 3. Remaining thing is nothing but 1 plus tan square theta raised to 3 by 2. So you can write this as g lambda into r square divided by this r cube over here. So we can cancel one r square and r square over here, into integration of, we can write sec square theta d theta divided by 1 plus tan square theta can be written as nothing but sec square theta raised to 3 by 2. So this sec square theta raised to 1 by 2 is nothing but sec theta, thus it's going to be sec cube theta, and sec square theta and 1 sec cube theta over here is getting cancelled. So we can write this is going to be g lambda divided by r into integration of 1 divided by sec theta d theta. And we know that reciprocal of sec theta is nothing but cos theta, so this we can write integration of cos theta d theta. Now we can put the limit of this integration. So let's say this angle over here, if we are taking this angle is means we are taking measuring angle from here. So if you are taking this angle is nothing but theta 1, and take it as the angle for this particular point is take it as something but theta 2. So we can observe that we are like first we measured angle in this direction, this theta we measure in this direction. So this we can take it as positive, and this we can take it as something but negative. So for this particular point angle is going to be minus theta 2. For this particular point angle is minus theta 2, and for this point this angle is going to be plus theta 2. So we'll integrate from plus theta 1. So we can integrate this one from minus theta 2 to plus theta 1. So we can put the limit over here. So if you are putting the limit from minus theta 2 plus theta 1, so we can write this is equal to g lambda divided by r. We know that integration of cos theta is nothing but sine theta, and the limit is changing from minus theta 2 to plus theta 1. So this is going to be g lambda divided by r into, if you are putting the higher limit as theta 1 minus lower limit as minus theta 2. So we know that sine of minus theta is nothing but minus sine theta, so it is g lambda divided by r into sine theta 1 plus sine theta 2. So this plus minus minus it becomes plus. So this will be the value of gravitational field which is perpendicular to the rod or a thread if its linear mass density is lambda and gravitational field at a distance, at a perpendicular distance, r from the rod. Now if you are considering an infinitely long rod, that means in some question they will give it as there is an infinitely long rod or infinitely long thread, then we can just observe how this limit is going to change. And if you are just considering a point P over here, and if it is extending up to infinity, and this point P is at a perpendicular distance r from here, if it is moving up to infinity, if you are drawing a line from here to infinity which is going to touch the end of this rod, then this angle is extending to 90 and this angle is also tending to 90. So we'll take the value of theta 1 is equal to theta 2 is equal to 90 degree. So we can write the value of gravitational field which is perpendicular to this one is equal to g lambda divided by r. The equation was g lambda by r into sine theta 1 plus sine theta 2. Over here theta 1 is 90 degree and the value of theta 2 is equal to 90 degree for an infinitely long rod. And we know that the sine 90 is equal to, so this 1 plus 1 we can take it as number 2, so it's going to be 2g lambda divided by r as the equation for a gravitational field which is perpendicular to the rod when the rod is having infinite length. Now we can find out the value of gravitational field which is parallel to the rod, so that we can find out by integrating this dg sine theta component. So integration of dg sine theta within the specified limit, so we can write this as g lambda into dy, same as like in the previous case, divided by r square plus y square, and the value of sine theta can be written as opposite side y, divided by r square plus y square raised to 1 by 2 over under root of this. So we can write this g lambda into dy divided by y into this can be written as r square plus y square raised to 3 by 2, 1 plus 1 by 2. Now again for integration purpose we can write as y is equal to, we can take it as y is equal to r tan theta. Then we are differentiating this equation, we'll get as dy is equal to r sec square theta d theta. Now we are going to put these values over here in this equation. So the value of g which is parallel to the rod is going to be g into lambda into dy. Instead of dy we can write this as r sec square theta d theta into the value of tan y over here. The value of y is nothing but r tan theta divided by, instead of r we can take it as r square, and instead of y we can take it as r tan theta. So this is going to be r square tan square theta. So same thing we are continuing, same as like in the previous case, is g lambda into r square divided by, if you are taking this r square outside, so this is r square raised to 3 by 2. This is going to be r square raised to 3 by 2 is r raised to 3. So r square over here and 1 r square over here get cancelled. Remaining things we can write like tan theta into sec square theta. The terms like tan theta into sec square theta d theta divided by, now the remaining term over here is 1 plus tan square theta raised to 3 by 2. Now same as like in the previous case, we can write as g lambda divided by r into integration of this tan theta into sec square theta d theta divided by 1 plus tan square theta is nothing but sec square theta raised to 3 by 2 is nothing but sec cube theta. So sec square theta over here and sec square theta over here get cancelled. So we can write this is going to be g lambda divided by r into integration of this tan theta into 1 by sec theta can be written as nothing but cos theta d theta. So we can write this is g lambda divided by r into this tan theta can be written as sine theta divided by cos theta into cos theta d theta. So this cos theta and this cos theta get cancelled, and same as like this in the previous case we can put the limit from minus theta 2 to plus theta 1. So we can write this as g lambda divided by r into integration of sine theta is nothing but cos theta, integration is sine theta is minus cos theta, and the limit is changing from minus theta 2 to plus theta 1. So we can write this as g lambda divided by r, or you can take this negative sign outside, minus of g lambda by r. We can put the higher limit, that is cos theta 1 minus cos theta minus of cos of minus theta 1 minus cos of minus theta 2. So we know that cos of minus theta is nothing but plus cos theta, so this can be written as minus of g lambda divided by r into cos theta 1 minus cos theta 2. Now if you are multiplying with negative sign, we can write this as g lambda by r into cos theta 2 minus cos theta 1 will be the value of its gravitational field, which is perpendicular to the which is parallel to the rod. Now here also for an infinitely long rod, same as like in the previous case, we can write theta 1 is equal to theta 2 is equal to 90. So the value of G parallel component will be equal to 0 because cos 90 is equal to 0. So just remember the equation for gravitational field due to a uniform rod at a point P, which is at a distance r from here, with respect to these angles theta 1 and theta 2. This angle we took it as theta 1 and this angle we took it as theta 2. So basically we are finding out two components, one component perpendicular and the other component which is parallel. And we got the perpendicular component as nothing but g lambda divided by r into sine theta 1 plus sine theta 2. And if it is infinitely long, then it is 2g lambda divided by r. And the parallel component is g lambda divided by r into cos theta 2 minus cos theta 1. And for an infinitely long conductor, the parallel component will be equal to 0. Hope so that you understood what were the things we discussed in this class. If you are having any doubt, please contact. Thank you.